Hello everyone, this video is going to review the two equations that we need to know for Friday's test and how we can use them to learn a little bit more about properties of different types of electromagnetic waves. The first of these equations relates the wavelength and frequency of a wave, and that says that the speed of light c equals the wavelength lambda times the frequency nu. One thing that's important to remember is that we have to have the proper units for all of these quantities. The frequency needs to be in hertz before it can be plugged in. The wavelength needs to be in meters before it can be plugged in. And then the speed of light c is a constant, equal to 2.998 times 10 to the 8 meters per second. And that speed of light is the same no matter what type of electromagnetic radiation we're talking about. So notice that since wavelength times frequency must always equal the same number, if the wavelength is bigger, the frequency is smaller. If the wavelength is smaller, the frequency is bigger. We're going to come back to that a little bit later on. As an example of a problem using this, let's say that a particular light has a wavelength of 5.00 times 10 to the negative 7 meters, and we want to find the frequency of this light. We know the speed of light, we're given here the wavelength, and we're trying to find the frequency. So we start by plugging in the two numbers that we know. The speed of light, 2.998 times 10 to the 8 meters per second. That equals the wavelength, which we've been given in meters, so we can go ahead and plug that in. 5.00 times 10 to the negative 7 meters times the frequency nu. And so nu is just like our x in a lot of your algebra problems. So to solve for it, we divide both sides of the equation by 5.00 times 10 to the negative 7 meters. And if we plug that in, we will find that to three significant figures, the frequency is equal to 6.00 times 10 to the 14 hertz. If we had instead been given the frequency and were asked to find the wavelength, it's exactly the same process. We would still start with the equation c equals lambda times nu. In that case, we would just plug in for c and nu, and we would be solving for lambda in exactly the same way. Remember, as I mentioned before, the frequency must be in hertz and the wavelength in meters. So one possible complication to a problem like this is perhaps the wavelength is given to you in centimeters rather than meters. You need to first do a unit conversion to turn it into meters before plugging it in. The other equation that we have is for the energy of a photon. And that energy equals Planck's constant h times the frequency nu. And here the energy is measured in joules, which is symbolized with a capital J. H again is Planck's constant, whose value is 6.626 times 10 to the negative 34 joules times seconds. And nu is again the frequency in hertz. Problems dealing with the energy of a photon are very similar to the ones that we just talked about between relating speed of light, wavelength, and frequency. There's a constant, Planck's constant in this case. We'll be given the value of one of the other two variables, either energy or frequency, and be asked to find the other one. So for example, let's say we want to find the energy of a photon whose frequency is 9.50 times 10 to the 14 hertz. So we know frequency, we're looking for energy of the photon. We start with E equals H times nu. Planck's constant is given to us, 6.626 times 10 to the negative 34 joules times seconds. The frequency is in hertz, which is the unit that we want. 9.50 times 10 to the 14 hertz. And so to the proper number of sig figs, which is 3, when we plug this in, we get an energy of 6.29 times 10 to the negative 19 joules. One other thing to note is that since both of the equations that we've talked about have the frequency in them, these equations can also be combined. So the most common application of that is we know that E equals H times nu, and we also know that C equals lambda times nu. We may want to find the energy of a photon whose wavelength we know, or from the other, going the other way, be given the energy and find the wavelength. One way to do it is to do it in 2 steps. Use this equation to find the frequency and then plug into the equation on the left. Or notice that if we divide both sides of the equation on the right by lambda, that gives us nu equals C over lambda. And we could plug that in for lambda over here and get E equals H times C divided by lambda. So again, that's not really a new equation. We're just taking the 2 equations that we already know and putting them together. I mentioned earlier that we can use particularly this second equation and the first equation actually also to learn something more about properties of different electromagnetic waves. So remember that we've divided up the electromagnetic spectrum into several categories. And the way that we arranged it initially was from high energy down to low energy. The highest energy types of electromagnetic waves are gamma rays. We then have X-rays, ultraviolet, visible, infrared, and radio as the lowest energy. But since we know that E equals H times nu, and H is a constant no matter what type of light we're talking about, high energy also means high frequency. So going from top to bottom also goes from high frequency to low frequency. But remember that from C equals lambda times nu, if frequency is big, wavelength is small, or the other way around. So the top of the list, gamma rays, would be the lowest or shortest wavelength, going down to the highest or longest wavelength at radio waves.